Hey, good morning. People funding Kickstarting, awesome. Kickstarter's great. Has anyone here ever done a project through Kickstarter? Like gotten something funded? Yeah, that would be cool to do. I've never tried that. I've wanted to. Um, Mom got a tea company kickstarted. Awesome. That's super cool. Yeah, if any of you are particularly excited by your SLPs, um, that's always a possibility. I mean, that's where new products and new ways of doing things come from. Whoa, cool. I'm trying to get back into tea. Someone got me some really nice tea for Christmas, and it's expanded my appreciation for um, interesting teas. Although the one with kale was kind of iffy, but yeah, I mostly do water. I do some decaf in the morning, but um, yeah, kale tea is a little interesting. Although there are worse ones too. Alrighty, so PA5 is graded, and really nice job across the board on PA5. So lots of hundreds, which is awesome. Lots of people, majority of people got the core of the code to work great, so they were able to find the maximum value and return that successfully. Um, and there was really sort of three aspects to PA5. First was getting the maximum value, and that was sort of the main point of the program. And then there was getting the item count, which is really, an additional task on top of the max val itself. And then there was the dynamic programming aspect, which is, adding some caching to speed up the calculations. Um, and so nailing all three of those, right, gets you full credit. But but the focus was on getting the max val. Um, is there such thing as a healthy amount of energy drinks? Energy drinks are an interesting term at all, especially the calorie-free energy drinks. Like, how does that work? Because a calorie is a measure of potential energy. So, energy drink with no calories is kind of from a physics perspective interesting. Energy free energy drink. How about a drink free energy drink? Energy air. Well, there are oxygen bars. And there are people who have supposedly learned how to live without eating. They like digest sunshine. But I don't know any of them personally. Yeah, flowers do it, right? So flowers are the super enlightened. So let me go through some sample code here for for PA5. Yeah, fasting will do that for you. Although yeah, actually 300 pounds in 300 days is doable. Yeah. Um, So just some sample code for PA5. So just to sort of nail down some of these lingering questions on caching and returning items, and we've seen pseudocode for most of this. So this is my version of PA5. So there's an answer structure, and this is the thing that gets passed back and forth, right, from max val. This comes back. This is what we store in our cache. And you really only need two pieces of information: a maximum value and the count of each item. So this is an array of integers, and element I tells you how many of item I you need in order to get this maximum value. And I also use the max val as a flag in the cache to know if I've actually stored a value at a particular entry. And I do this by using the fact that max val should be positive for a meaningful value. So here's the cache, right? And it's just an array of these struct answers called save. And I pre-wire element 0 to have a value of 0 just so that I can return that when I don't have an answer that I want to return. So this is where I'm going to store the inventory. It's going to be an array of these structures, which has the weight, the value, and the name for each item. And then the boring function prototypes as usual. So inventory inv, that's an array of struct inventory. That's the thing that I'm going to read in from the file to tell me about the objects that I can choose from. There's the length of that array, and arrays you always need to know the length. Now, a lot of people coded up their inventory to basically initialize something in here to 0 and then use that to tell you when you're at the end of the array. And that's not a bad way to do it, but the other option is, just have a separate variable that tells you how long your array is. That goes away in 223, by the way. When we get to Java, Java actually understands arrays as a pretty basic element of the language. So arrays come with, a notion of length and so on. So we'll have more fun with those. Yeah, it makes life good. So many things about Java make life good. All right, so temporary variable and the not so interesting argument check. So make sure you've got 3 arguments. If not, print an error message. And I'm doing fprints to standard error. And we don't really talk about this a whole lot. We touch on it a little bit in 224, but basically you've got 2 output streams that you can write to: standard out and standard error. They both show up on your display. The difference is if you redirect standard out and you write something to standard error, it doesn't get redirected. So if you run a program and you just say greater than output file, or you pipe it into something else, but your program prints a message to standard error, you'll actually see it on your display. It won't get redirected. That's useful and pretty standard when you're trying to produce messages that it's important the person see, instead of producing output that the person might want to redirect into a file or another command. So usage error, right? Print out a message, tell the person how to use the program. Otherwise, scan your first argument and see if it's an integer, and if it's not, if it doesn't return 1, print the usage message. And then if the capacity is illegal, so less than or equal to 0 or beyond the max capacity, give them a message reminding what the capacity should be. Otherwise, we're all set. Initialize the cache. So this is setting the max values in the cache to let me know whether or not a value's actually been stored there. And then read in the inventory. So argv2 is the name of the file we want to read from. inv is the array of items it's going to load into, and this is the length, which is returned by the read function. And if anything goes wrong in trying to ingest, my read inventory will return a 0. And so I can use that to send an error message saying, hey, there's some problem with the inventory. And then echo. So this just prints out the inventory and the capacity of the bag. So that's just showing us what we read in. Nobody in here is a coding noob, by the way. You're a noob maybe when you're in CSE101 if you haven't done any coding before. But at this point, I would say everybody in here is basically a programmer. Because you can debug and you can write code and you can do data structures and you know, you're ready to go on to object-oriented programming, which is like super big league stuff. But you know, when you can program in C, you're a programmer. This is the nuts and bolts of it, right? Everything else is easier than C, more powerful and easier to use. So yeah, you're definitely advanced at this point. All right, so echo the inventory and the capacity, and then just call the maxval function to get the answer and print out the answer. And it's worth noting that, you know, my main program is pretty small, right? It's basically this. It doesn't actually do anything by itself, right? I mean, it does some serious parsing of the input, but you know, all the hard work is done by other functions. But in terms of writing this and developing it and debugging it, right, this is just a bunch of function calls. And so this is top-down design, right? You start with a main program that assumes you have all these other support functions, and you just call those, and the main program basically decides, what do I want this program to do? Well, initialize our cache, read in an inventory, show me the inventory, calculate a maximum value, print the answer. That's a pretty high-level description of the main program. All right, so then you got to start actually like writing the code to do these things. And maxval is, you know, obviously the trickiest one, echoing the inventory and stuff like that, not too bad. So maxval, so it takes the inventory length, which always goes with the array, and the capacity. And this is basically the code that we've spec'd out in lectures before. So if the capacity is less than or equal to 0, you can't put anything in the bag, and so we just return this value that I've preset to be 0. So a max val of 0, count of each item is 0. Otherwise, we're ready to calculate the value for this capacity. Let's see if we've saved it. And so this is one of the two things that get added for dynamic programming. This check at the beginning to see if we've calculated this value before. And at the very end, we have a matching statement where we'll save our answer before we return it into our cache, our save array. And then all of this in between, this is what you do regardless of whether you're doing dynamic programming or not. So I initialize a flag that I call max to -1. I'm going to set this to whatever maximum values I calculate. It's just a cheap way of knowing if I actually calculated any maximum values along the way. So go through all the items in your inventory, right, which is, you know, inventory length items. And this is, you know, what we've been talking about. So if the weight is less than or equal to the capacity, so it fits in the bag, I calculate a diminished capacity, which is the original capacity minus the weight of item I. And then I find a temporary answer by calling maxval. And, you know, the first two arguments are the same, but I ask it to calculate for the diminished capacity. And I save the result in temp answer. I bump up the item count for item I, so I increment that. And then I add the value of item I to the maxval and temp answer. So temp answer is the solution if this was the optimal way to start putting things in my bag. So let's find out if it's better than what we've seen. If its max val is better than our max, then I'll go ahead and I'll set max, just to remember that, and I'll save temp answer and max answer, which is a local variable. Now there's a lot of ways you could have done this. You could have combined a lot of steps together. I've got this broken out into a bunch of individual steps, right? For example, calculating the diminished capacity and then passing that here. Well, you can just pass cap minus inventory I weight as this argument and not have to type this line. But I did this basically so I could, have a comment saying this is the new capacity. So most people, their code was shorter than this inside their max val loop, which is fine. All right, at the very end, if my max is still equal to -1, it means I never called this, which means none of my items fit in my bag. And so I just return a max val of 0. Otherwise, max answer is my best answer. Save that in your cache and then return it. And then the rest is closer to CSE222 stuff. So reading the inventory from this file name. So open the file, make sure you were able to open it, and if not, return an error message, right, which we do by setting a length of 0. Otherwise, iterate while you read in from the file into a buffer, scan it into these 3 pieces, and if the scan doesn't return 3, then something was wrong. Print an error message and return 0. And a return of 0 tells my main program something went wrong, don't continue. Otherwise, bump up the inventory length. If the inventory length is too big, print an error message and return 0. Right, and any of these return zeros, that'll basically end the program inside main. Otherwise, go ahead and close the file pointer and then return the inventory length. Now I've got memory leaks in here. I should probably, close the file pointer here and so on and so forth. But I was able to get my output identical to yours. Excellent. Yeah, it's a really kind of acid test way to make sure that your output's doing the right thing. Yeah, I forget to close files too, and like memory allocations, they get closed by the system when you exit. So it's not really a problem. All right, initializing our array of answers, so our cache, right? So just iterate. For each one, I set the max val to -1, set the item count to 0. And then I went ahead and set a special value in element 0, so I could return that for my non-solution. Until you code for a Raspberry Pi or an Arduino. I think on a Raspberry Pi, since that's basically Linux, I think that's still going to free your memory when you exit. Arduinos, I don't know if you can do a malloc in an Arduino, because I don't think there's heap storage. But if you had, a small kind of standalone microprocessor that you could allocate memory on that wasn't sitting on top of a full OS, yeah, then you'd probably have a problem with memory leaks. PIC processors, the only one I've ever played with is the one that you use in 270, the 18F1220, and that's does not have an operating system either, and I don't think it comes with a heap. But I'm thinking, if you used a Raspberry Pi but you didn't run Linux on it, you just decided to make some sort of minimalist operating system, you might still have a way to allocate memory, and then you'd need to free it. Stack space is an example, right? So if you don't free your stack space in Linux, right, your stack goes back to normal when your program exits. On a PIC processor, if you don't manage the stack correctly, you can get a stack overflow. So, because your program basically never exits on a PIC. So the rest of this, I don't think there's anything interesting in here. So the echo, just loop through your inventory and print. And then final answer, either say there's no solution or print the max value and then go through and show the items that make it up. So the real workhorse in here is the max val function. Um, but the inventory count comes from um, basically this right here. Keeping track of a count of items, and then when you find a solution that you get by starting with item I, make sure you add 1 to the count of item I in your return from the recursive call to max val. And then the dynamic programming, the caching is, check the cache in the beginning and save into the cache at the end. And again, don't change anything inside here to add dynamic programming. All of this stays exactly the same. It's just one check in the beginning and one save at the end. And so one of the tests I ran was using a bag capacity of 1,000 and an inventory of 10 items. And if you don't have the caching set up, that just, sits there and takes forever to run. And so that jumps out. All right. I did not take off points for having the program named incorrectly, for not having sufficient comments, for not having your name in the program, all of that kind of stuff, right? But most people, had well commented code, named the program correctly, good stuff like that. So definitely keep up those habits. If you're practicing with code over break, right? Try to keep in the habit of writing code that's production quality, which for us means something you would turn in for a grade. So indenting or some kind of consistent style, commenting, organizing it well, and so on and so forth. Basically the stuff you've been doing all quarter. Looks really good. All right, so any comments, questions, concerns on PA5 or anything else up to this point? I feel like the amount I comment for a grade is excessive. Is there like a minimum we should be doing? Let me see. So just looking at your code, so yeah, having a comment about a chunk of code is definitely key, right? If you're about to do something like you've got a balance function, right? So the first thing you're going to do is check to see if the root is null. You can put a comment on the same line saying, base case, leave here without recursing. You can put a comment before that, right? You don't necessarily need to do both of those. And then a comment saying, check the heights of the left and right subtree, make sure they're close. And, if your next few lines say, if the height of this minus the height of that is less than or equal to 1, you don't really need a comment on that line saying, the heights are within 1, right? So yeah, before a few lines of code, you can have a comment saying, what is the purpose of these next lines of code? And the real kind of guideline is, if you have 3 lines of code, is it really clear what they're doing? Right? So if you're about to, test 3 conditions, you can have a comment saying, make sure A, B, and C. And then you don't really need to comment the three statements that check A, B, and C, right? Unless there's something unclear about how those are being checked. Um, yeah, see. Um, and I've been encouraging people to err on the side of having too many comments in this course, just because I want people to explore, kind of the space of how can you document your code. Um, and in some courses, at universities, you'll actually be encouraged to not put in too many comments, or to not put in spurious comments, to not comment out debug statements, but to actually delete them. Where an instructor wants to actually see just the code itself and the necessary comments. Same thing when you're working in industry, right? You're not going to want to leave in commented out debug statements in the final code that's being merged with something else. But at this level, right, I'm more comfortable erring on the side of lots of commenting, leaving in your debugs and commenting them out, and so on and so forth. I generally am not going to ask you going forward to comment your functions the way that we've been commenting them. But I want to make sure that you've had experience doing that, because in some cases that'll be a requirement. But writing code for yourself, or if something is just being turned in for an assignment, don't necessarily need that big comment block in the beginning with all the inputs and outputs and so on. And yeah, some comments in industry might be superfluous and annoying. I mean, I always put song lyrics in my code when I was in school, because I was always listening to music when I was coding, and I was usually pretty tired, and so I would just kind of like free associate. And so, a lot of my code had lots of random Pink Floyd lyrics in it mostly. And, I don't usually do that if I'm writing code for somebody else. But it still helps when I'm debugging, to go back. It's like sometimes I would recognize my code by the music I was listening to when I, spent an hour working on this one bug. But at the very least, right, make sure you put in comments explaining what a section of code is doing, right? And if it's clear to somebody who knows the language how that section of code is doing what you've described, then you probably don't need a lot of comments in there. Yeah, exactly. All right. Well, let's talk about the final a little bit. So again, your final will be on Monday, 10 o'clock to 11:50. I always recommend that you come into Zoom and hang out in the room. You can turn off the sound if you want, but just in case there's corrections or comments on questions, right, I'll post them in chat or occasionally use my microphone. And so, sometimes there's a question that's impossible to solve, and I'll put a note in chat and say, hey, question 7 should be such and such. So hopping into Zoom during the exam is useful. I'm not requiring people to use their cameras during the exam, so, if you don't want to be in Zoom, that's fine, but there's no way for me to give you corrections and such. So 10 o'clock to 11:50. I was going to say question 87 just to scare people, but I didn't. And similar in style to the midterm. So it will be a PDF file that you'll see in Canvas. It'll be available starting at 10 o'clock. and you'll need to type up your answers, save them as a PDF, and submit that by 11:50. The exam will not automatically close at 11:50, so make sure you submit on time. There's no countdown timer, but I'll have some kind of horrible penalty for every minute it's late again, just to make sure people take the deadline seriously. And the same general setup as the midterms. So there'll be mostly programming questions, point wise. Most of the points will be writing code, which may be whole programs. It may be snippets of code. There might be some analysis of code. There will be some non-coding questions. I'll probably ask you to do some things with heaps or hashes or stacks, or doing some sorting or things like that. 5% every minute it's late. I forget what I did for the midterm. I think it was worse than that. I think it was like 10 points a minute or something. I don't remember. Probably not a lot, if any, of multiple choice. But be prepared to do some things like, show me the steps of some sorts, manipulate heaps, build a stack, build a queue, stuff like that. Right? But definitely programming questions. And it covers the entire quarter, so everything back to the beginning, including linked lists and all of that stuff. But certainly, a bit more emphasis on the stuff we've done since the midterm, which has been, a lot related to trees, and a lot related to recursion. So you can expect to see good doses of that. And so I posted a list of possible topics, and this is, not based on the exam, which I haven't written yet. But it's just kind of, going back and thinking about what we've done, just kind of trying to hit some of the main points. So we can talk through these, but again, if you have any questions, right, it's more meaningful probably to talk directly about things you want to go over. I am not going to ask you about AVL trees. Okay, we talked about those briefly this week, but I'm not going to ask you to balance a tree or calculate balance factors or something like that. I wanted you to see it in class, but I won't put that on the exam. But pretty much everything else is fair game. Yeah, that's a good strategy for exams in general. All right, so abstract data types. This is a concept. So here's what I mean by an abstract data type. For example, suppose we're making a linked list. Well, let's do a tree. We've been doing trees lately, right? What is a tree? Well, when we implement a tree, it's a struct node with a pointer to the left and the right, and an initial value of null. And, if it's a tree of license plate, then it also has, a plate, a first name, and a last name, which are car stars, and so on. But those are not what a tree is in an abstract sense. That's a particular tree. That's the tree for PA4. If we make a decision tree, we would have nodes called yes and no, and we could store information in there, and we could traverse it in a certain way, and so on. But as an abstract data type, a tree is a collection of information, right? Where information can be stored in the tree. We can search the tree. We can get information from a tree. We can delete nodes from a tree. So a tree might be something like, we have a way to add, we have a way to search, we have a way to delete, we have a way to traverse, we have a way to, release, maybe we have a way to initialize, right? And these things have nothing to do with how the tree is implemented. I should never have to know that your left child is called left. I should never have to know that your data is called data, or your data consists of 3 character strings, plate, and first name and last name. I should never have to know that the license plate name is dynamically allocated at runtime, right? Those are implementation details. At the user level, right, a tree is just this data structure that you can do these things to. And so when we write a main program, we interact with our tree through, a series of function calls. And those function calls interact with the lower level details of how the tree is implemented. So in the linked list example, the first 2 programming assignments, the first one we implemented a linked list using an array. In the second one, we implemented a linked list using nodes that we malloced and having pointers. Our main program didn't really have to change a whole lot. Right? When we wanted to add something to our list, we just said add. And when we wanted to search for something in our list, we said search. And whether our list was implemented with arrays or with, dynamically allocated blocks of memory, the way we use the list doesn't change. So when we talk about an abstract data type, we're thinking about the data type, the data structure, from a user perspective, as opposed to thinking about it from the point of view of how it's implemented. Does that make sense? And it's really just a conceptual thing. But when you're writing code, your main program, if your main program is dealing with low-level details of the data structure, if your main program is calling malloc and setting left and right to null, then it's not dealing with your tree as an abstract data type. It's actually dealing with how you've implemented your tree, right? Ideally, your main program would say, initialize or add a new node. And those functions for initializing or adding a new node, those would do malloc, those would, check to see if a node is null, and so on and so forth. So it's main program, and there's some kind of interface, and there's some kind of implementation. So the version of this tree that you see at this level, that's the abstract view of a tree. All right. So we can just sort of start at the beginning here and go through this. So, everybody here knows what a structure is. You know how to make a structure statement, right? You've been doing this all quarter, so that's all fair game. So defining a structure, making sure you understand the difference between something that's a struct and something that's a pointer to a struct, right? And you've done this, to the nth degree, especially in PA5. You can make a struct node, which, is a thing that has all these different fields to it, or you can make a pointer to a struct node. And the pointer is just, saying, at this memory location, you'll find a struct node. If you make a statement like, so you've defined a type of structure in a struct statement, and if you say something like struct node x, right? That's a compile time declaration of a variable named x, which is a struct node. And if a struct node takes 100 bytes, this will allocate 100 bytes and make X, a reference to that 100 byte block. There's no need to do a malloc. The compiler and the linker will set up storage for this structure, and X will refer to it. But if you say something like struct node star pointer, right, this is just a reference to a struct node. It's a memory address. And if I try to use this as a struct node, I'm going to segfault. And so here we usually say something like pointer equals malloc, so that it actually allocates space for this and then sets pointer to be a reference to that. All right, so that's allocating memory for structures. Accessing fields, so if you have a structure, right, you can get to a field by just saying x dot, whatever the field name is. If you have a pointer, if I were to say pointer dot field, that's a syntax error, because pointer is not a structure. Pointer is just a pointer to something. What it points to, that's a thing that has a field. So this is legal syntax, but not syntax you should be using. What you should use is this. Right, and that means the field part of the thing pointed to by structure. And I have a few people who turn in code that uses this, and I don't know if they're being ironic or if they don't know this. And I haven't taken off points, but I can almost guarantee that at a university, if you turn in code like this, you'll lose tons of points. So yeah, use this for dereferencing fields from pointers. And don't use this if X is actually a structure. So if I tried to do, X arrow field, right, that's going to give me a compile error, because it's going to say X is not something that's a pointer. It's just a structure. And then arrays of structures are just like arrays of anything else, right? We could say struct node X bracket 10, which would make us an array of 10 struct nodes called X. But remember, arrays can also be defined by using a star. And this is where things can potentially get confusing, but I don't think they have to at this point, right? If we want an array of struct nodes, we can do that. If we want 10 struct nodes, this will set it up for us. But if for some reason we want to set up an array at runtime, then you get into the funny business where you do something like this. So is this a pointer to a struct node, or is it an array of struct nodes? It's actually both. Right, and this is the whole thing of arrays and pointers in C. So if I set this to malloc 10 times size of struct node, right, now X is technically an array of 10 struct nodes. And if I do X bracket 0, X bracket 1, X bracket 9, each of these is a struct node, which means I can do something like, X bracket 3 dot field, and that's totally legal. If you wanted an array of pointers to struct nodes, that's a struct node star star. We're not going to do that. But if this makes sense, you're all set. If it doesn't, you're probably still all set. All right, and that's the business of dot and arrow, basically. Right, so dot gives you a field from a structure, arrow gives you a field from a pointer to a structure. All right, so linked lists. We are not going to talk about linked lists implemented with arrays. That was an exercise in PA1, but that's not how linked lists are ever really implemented in the field. And I'm not going to ask you questions about that. So when I talk about linked lists, we should always be thinking about nodes that include pointers to other nodes. And the linked lists that we developed almost always had a sentinel node. Sentinel nodes are not required for a linked list, though. You can make a linked list where an empty list is null and the first node is the actual first data node. But we typically create a sentinel node whose purpose is to point to the first data node. And then an empty list looks like this. And it's just a way to deal with edge cases. So you know the basics, so we can make linked trees. Yeah. And you can make a tree with a sentinel node also, but we don't because it breaks the recursion. And if we try to do recursion on a linked list with a sentinel node, it gets tricky too. Double tree. And in our linked list, we mostly worked with linked lists of integers, right? But in general, you know, there's a data field. And there's a next field. This data field can be anything we want. We typically make this an integer when we're doing linked lists on paper. Right, we'll just pop an integer in here. But this could be anything you want, including a pointer. And if it's a pointer, it can point to anything that you want. So this could be a pointer to another list. This could be a pointer to a binary tree. This could be a pointer to a heap. And so we could make a structure that was a linked list. Like this. And each of these data fields could be the sentinel node to a linked list. Right, so a linked list is a simple structure in itself, but these fields could be, you know, pointers to something complex. They could be arrays. They could be two-dimensional arrays. They could be an array of pointers to hashes, right? Makes no difference. Now in C, this gets really complex sometimes trying to bundle this together. In Java 223, this is going to be absolutely delightful. Right, once we start working with objects where we can bundle functions and data together, this is going to be, you know, delightful to play with, basically, once we get our brains around it. Can you draw a linked tree in less than a minute? I'm still not sure what a linked tree is. Are you thinking like a linked list of trees? Or tree, fair enough. I can think of a few things that it could be. You could have trees where your roots are sitting in a linked list. That would be kind of cool. You can make a tree of trees. You can make a tree where each node, you know, is itself a binary tree or an n-way tree. And yeah, we do talk about forests of trees, actually. It's a computer science topic. All right, so we'll mostly go through this tomorrow. So we'll rehash linked lists, talk about ways to pass variables, and go on from there. So, but take a look through this on your own, and if there's anything you definitely want to talk about, you can ask about that in the beginning of class. We can make sure we get to it first. Happy little trees, no accidents. Exactly. All right, cool. Have a great afternoon. I will see you tomorrow.